Justin Downs. Justin, there you are. Can you share your screen so you can present?
Yep, hold on. Okay,
there you
am I
go.
sharing?
Great.
All right.
Yeah, perfect.
Thanks. Yeah, so it's great to be here with you all today. I'm fairly new to this field, so it's awesome to hear from the people directly that I've been sort of reading books and papers on for the past year or so. So this is some work I've been doing. I'm in grad school right now, so over the past semester about how to simulate networks that were grown by preferential attachment type models. So first off, like, why do you want to simulate networks? So it's hard to collect real data. Real world data can often be massive. You don't have access to it. The privacy issues, you don't want to collect all people's attachments and friends and their names and their emails. We also want to test our theories. So when you have a real world data set and you build a model for it, often you don't know if that model is robust to other types of data that are similar. So what are some of the goals? In this specific example, I'm trying to mimic degree distributions, but you could also try to mimic the topology of the graph. So features of the graph itself, like the width or the centrality of the graph, or attributes of the nodes. So, people's ages, people's preferences, political leanings. So a lot of this work arose from a project I was involved in a few years ago that sort of exposed me to these ideas of computational social science. And it was the DARPA Social Sim project, which I'm not sure, maybe some of you were involved in, but it's the computational simulation of online social behavior. So this is stuff we were doing is given a real world social network at a certain state, could you predict the structure of that network at a future state? So we would collect, so back then, the specific data we were working with was the open source GitHub data. So, what projects people are subscribed to, who commits to what projects, how projects are newly formed. So could you predict those structures at a certain point in a future point? So a simple way to simulate these networks is preferential attachment, which I'm sure everyone's familiar with. Nodes with higher degree are more likely to get new edges. It's the Barabasi-Albert model. And we also have some modifications of these. So in this study, I looked at these three models: the base preferential attachment model, the Bianconi-Barabasi model, which adds a fitness value. So this fitness value is like a weight of how likely a node is to attract a new edge given a new node added to the network. And then the third model I looked at was the relevance model. So this adds yet another feature. It's a relevance function, which tends to decay a node's relevance. And so think of this as a node ages, it becomes less and less relevant. It is less and less likely to attract new nodes. I believe this arose from citation networks, where it was as the papers get older and older, they decay. Now, obviously, that's not true for all papers. Some papers are very robust to this as they stay relevant for an extremely long time. So I coded out these models in Python and plotted what the degree distributions were for these three different models and how they look. I plotted here the power law of exponent 2, so you can see sort of a reference frame. And so the goal will be to evolve these networks. So the thing about these network growth models is that they add nodes at each time step. So in order to maintain this degree distribution, they're sort of reliant on adding new nodes to the network, and the new nodes, the law of large numbers, these new nodes eventually get you to the degree distribution that you see. So we want to evolve these networks. So maybe not like citation networks, but real world social networks. You don't just come into the network and create your edges and then that's sort of static. As the network ages, you are adding and removing edges at each time step. So we want to evolve these in a way that follows sort of the base model, be it the preferential attachment or the relevance function or the decay function, such that nodes can add and remove edges while new nodes are being added to the edges. So what I found is if we just follow these same principles, so we randomly remove edges and then we grow edges on existing nodes, but following those same rules, the degree distribution tends to go to a normal distribution, as you can see on the right, versus what was expected in the previous graphs. So my initial work was to figure out a model to evolve these networks that still followed the same degree distribution. So where did I go wrong initially? I initially thought that each model would have to have its own evolution mechanism. So especially with the fitness function, I thought I would have to find a way to evolve a node's fitness function such that the degree distribution was maintained, or evolve the decay function as well in a similar technique. Those generally ended with failure, so all the distributions regressed back to a normal distribution. So I sort of went back to the drawing board and I just settled on one simple model that evolves all three networks. So here's the algorithm I developed. So we select a k number of nodes to have their edges in the network grown, and we select nodes for those, so opposite edge nodes for those k nodes using the normal preferential attachment, and then we create edges. So these k nodes have their edges grown similar to as if they just joined the network, fresh using preferential attachment. Then we select k nodes to decay. Now from those k nodes, we get all the edges that are connected to them, and we get the set of the opposite, V nodes, and we select. So this is the thing that took me a lot of trial and error to come through, is to select one edge to delete to the inverse of the preferential attachment, but just on that subset of nodes that are connected to the node we've selected to delete, and then we delete that edge. So here's the results after 300 iterations of evolution, with about 1,000 edges added and deleted at each step. And I don't have it here. There's about 10,000 nodes in the graph, and it was grown with 3 edges added each time. So there's approximately 30,000 edges in the network, and that ratio is roughly preserved since we're removing and adding 1,000 edges at each time. So that's where I'm at now. So this is sort of initial work. I hope to continue it over the next semester or so. So what's next? These models are generalizations of real world behavior. And they're not modeling anything sort of specific in the real world. They're just trying to recreate a metric. And so in this case, the degree distribution. So can we develop ML models where this metric, operates sort of as like a loss function? And so what would these look like? And so this is what excites me about the field. So for my day job, I generally do machine learning. So develop models, and work with data to make machine learning models. So I remember years ago reading the book Thinking Fast and Slow, which introduced me to the concepts of type 1 and type 2 thinking. And what brought me to this field is where machine learning is at right now is mostly type 1 thinking. So it's like things you can do automatically. You know, I can recognize that's a cat or a dog. I can transcribe. I can understand you know, parts of speech, you know, without thinking about it. And even the things that are considered, you know, sort of most complex machine learning out there are also sort of type 1 thinking. So like driving a car, even though it requires a lot of skill, it's something that us as humans we can do without really thinking about. But when we get into these agent-based systems, especially like reinforcement learning models, where agents are making decisions based on expected future states of the environment, is really type 2 type thinking. And I think that's really the future of machine learning and sort of agent-based models. So I'd love to use reinforcement models where you know the reward function or the loss is, you know, how well we can discover these agent behaviors that end up in recreating the metric that we're looking for, like the degree distribution. I think my future work, I will not be able to just jump right into RL models. Probably have to start with ABMs or recurrent neural networks to evolve networks through these agent decisions. Oh, yeah, and that's all I got. A pretty short one.
Great, thank you for that, Justin, for sure. So we definitely have some time for questions if there's any questions out there. So what? So just what's the long-term goal for this project? Like, where do you want to eventually get with the use of this study?
Yeah, so this study sort of arose from stuff I do at my job, you know, machine learning, where we are starting to get into pattern of life analysis. So given the behaviors that people exhibit that we can measure, moving about through the environment, this is mostly spatial models and connections, where the connections are at a minimum, we're at least physically close to each other, but maybe we have some social network type data. Can we simulate data so that we can augment our data sets such that we can actually train these deep learning models? Because we'll have a data set and, you know, it may have 100,000 data points and we can train a model off of that. Will that model work for any other similar data set? We don't know, and we don't have the ability to collect another data set. So probably better to train on fully synthetic data and see how well our hypothesis works on this real world data set, which is sort of the beginning of this. And a lot of the work we are doing now is trying to create mechanisms to create synthetic data sets that accurately reflect the real data set.
Right, okay. So I see that we have a question from Sarah. So Sarah?
Can you hear me?
Yeah,
Yes.
yeah.
So I have a question. Very interesting work, first of all. Second of all, have you ever considered having the nodes be heterogeneous? So they have slightly different characters or values and such that
Yeah.
is preferential based on how similar or dissimilar they are to each other.
Yeah, so that is in the Bianconi-Barabasi model, sorry if I pronounce it wrong, where it has this fitness value that is sort of a weight. So think of that like popularity mixed with age. So the older a node is, obviously the more chances it's had to add edges throughout its lifetime in the network. But then you have this fitness value, which also makes some nodes more popular and some nodes less popular. And a lot of my initial dead ends were creating mechanisms to evolve that fitness value. I'm sure there's something in there, but I didn't quite crack it. But yeah, so quick short answer is yes. There's like a fitness weight in there.
All right. And do two nodes that have different fitness values, how does that affect their connection, their possible connection?
Yeah, so let me share the screen again. Yeah, so you see this fitness value. So the chance of a new node getting attached to an existing node it is a factor of it's preferential attachment, so this K value, which is how many nodes it's already connected to, but also this fitness value is weighting. So, and that's in relation to all the nodes in the network. So if someone's twice as popular, they'll be twice as likely as another node to get an attachment, but it's still like probabilistic. So it may not result in that actual behavior.
All right, that's very interesting. I'm only asking this because I'm working on an agent-based model in which, but it's not network, it's just pure aggregation and fragmentation dynamics. So where two nodes attach if they are more similar or dissimilar, like depending on how similar they are to each other. So each node has a character value, and then they attach based on their common interests. You can think about it like that.
Right. Okay. Yeah, that's similar to what I was thinking for like next steps would be, actual agent behavior. So here agents are creating edges, probabilistically, but in the real world, they're creating it for some other real motivation. And so, obviously we have the same interests, we're more likely to connect.
Yeah.
So
Right.
yeah.
Thank you.
Thank you.
Thanks. Sharira, I saw you had a question.
Thank you for your presentation. It was great. At some point, you were talking about system 1 and system 2, two types of thinking.
Mm.
I'm curious to know your idea about like agents that have a dual process mind. I mean, they can act as if they are thinking in type 1 thinking, or they can also have like serious reasoning about the situation, so they think in type 2. And there are some heterogeneity between their agents' ability to switch to type 2 thinking. In experimental economics literature, we have this cognitive reflection test, which measures something like the tendency to think in system 2. And there is a heterogeneity. There are individual differences in this cognitive reflection ability. So what do you think about agents that are capable of thinking both type 1 and type 2, but some people tend to use type 2 thinking more, and some agents tend to use type 1 thinking more? So what are your ideas on that? I'm just curious.
Yeah, I guess I haven't really thought about that, but it makes sense, even if you just think of like real people. Like some people are very quick to react without being introspective. And so I guess, they have like a low emotional intelligence and they just react instantly based on, something reasons they don't even know, but some people are more deliberative in how they act. And so I guess it makes sense, yeah, to have agents that also, some react instantly and some react exploring the decision tree of the implications of their action even more. Although I've never seen stuff about that, but it makes complete sense to me.
Thank you.
Awesome. And I think I saw Juan's hand up next. So Juan.
Yeah, thank you, Justin, for your presentation. And you mentioned that when you see in the future is using more reinforcement learning to explore options in your research. I'm curious about in reinforcement learning, you usually have this like map of the potential future actions that an agent may take, and against that you like estimate the reward. But in these kind of like generative situations, there are multiple futures, and the analysis of that potential rewards, it becomes computationally prohibitive. I wonder if you have this issue in your experiments, and how do you sort out that?
Yeah, as far as exploring, so running simulations that explore possible possible like model states to determine like the optimal one. Is that what you're talking about?
Yeah.
Yeah, so we do this a lot at work. You know, generally we call it like hyperparameter optimization. So running, you know, dozens, thousands of models at the exact same time with different settings, and the techniques we use in the machine learning space actually are very similar to what have been talked about a lot here. You know, genetic algorithms. That space lends itself well to that type of you know, flipping parameters on and off. You know, transposing different parameters to the self. For reinforcement learning specifically, I mean, that's just sort of like, from my experience and from, you know, reading about the stuff that's especially done in like the video game space, that's just sort of like the cross to bear of doing reinforcement learning. You're going to run these massive, you know, computations that, you know, take an insane amount of time and cost quite a bit of money. I would like to explore, you know, ways to optimize that, but yeah, that's a little bit beyond me right now.
All right, thank you.
I'm muted, sorry. I think we have time for a question from Kuldeep as well.
Sure, thank you, Bill. Hi, Justin, thank you for this interesting work. Could you please go back to the slide where you have your own algorithm for the generation of network and decay? Yeah, wonderful. So I was wondering if you you have any thoughts on using discrete distribution rather than uniform distribution for decay function as well. If you have already, my understanding is probably you can do this in one step rather than two steps. You have any thoughts or any ideas about that?
As far as selecting the K nodes to decay, or selecting the edges to remove?
Well, when you do first step, uniform select K nodes to
Yeah.
grow. If you do, I mean, discrete selection rather than uniform, then probably you can control your uniform selection by incorporating decay within that distribution. Is that something that you have any thoughts about?
I have not, but I will explore it when school starts back up. Thank you.
Okay, that's great. Thank you so much.
Awesome. So great set of ideas there for you to take a look at for sure, Justin. And thank you very much for your presentation. I think at this point we can move on to our